We'll now talk about this notion of an apparent weight. Now, this is something that you would have experienced if you riding in an elevator. Now, suppose you were to take a weight scale into an elevator and you were standing on a weight scale in an elevator, which was moving up or down or at rest. One thing you will notice is that your weight scale, which could show you different readings depending on the state of motion of the elevator. Okay, now and this is now when I talk about weight scale, just remember that the typical weight scale that you buy from the store, of course, is technically a mass scale. It tells you your mass. Even those scales will show you a difference in readings if you take it into an elevator. A true weight scale would be something that you see out here. If you can see this picture clearly, this is a weight scale which shows you a mass reading. It is a mass scale. It tells you the mass, and it also tells you your weight in newtons. Remember, weight is a force measured in newtons. Mass times the acceleration due to gravity. So if you take this particular scale, which is a spring scale, and if you were to hang a 1 kilogram object from it, 1,000 grams, it would read around 10 newtons. Again, makes sense because weight is m times g, and g is about 9.8 meters per second square. But that's beside the point. If you take a weight scale into an elevator, and you're riding in an elevator and you're standing on a weight scale, you will notice different readings depending on the state of motion of the elevator. In fact, you don't even have to take a weight scale. You will experience different forces, a force whose magnitude can change depending on the state of motion of the elevator. Now, why is that? And that experience is what we call apparent weight. Let's start off. Well, what exactly is the weight? Well, we know the weight is the force that the Earth exerts on an object, and the weight is just m times g. Magnitude is m times g. It's the force with which the Earth pulls down on an object. Now, here is a person riding an elevator, which is, say, moving, which is either at rest or moving at a constant velocity. Either case, we know that the person and the elevator are in equilibrium, which means the net force acting on them are. Let's focus on the person. The net force acting on the person is zero. So if I were to ask you to draw a free body diagram for this person, that's the picture you would draw. You would draw the weight acting in the downward direction and the normal force, which is the force that the floor exerts on the person in the upward direction, and these two forces have the same magnitude. So let's state that here as well. Since there is no acceleration, we know that the weight, our focus is going to be on the normal force equals the weight. Okay. Now, when you talk about the weight, it's a force that the Earth exerts on any object. One thing to note here is that weight is not a force in terms of your experience of forces. If somebody were to come and push you, you can feel that force because you can feel that push. Now, weight as a force is not something that you directly experience. So weight is not a force you experience directly. What you directly experience is, yes, there is this force that the Earth exerts on you, but what you are experiencing is when you're in an elevator is what the floor is exerting on you. So what you directly experience is the normal force. You can feel it in your knees. That pull. You can feel it in your knees. So you in fact experience what, or let me just say what you experience is the normal force acting on you. And in fact, the normal force, so if you were standing on a weight scale in an elevator or anywhere, the normal force is also the force measured by a weight scale. Okay. And when we're thinking of a weight scale here, like I said, think of it as a Newton scale, which actually is calibrated in newtons. Okay. So that normal force is, so when you're looking at that reading on your weight scale, what you're really measuring is not your weight, but rather what force is that surface, that floor exerting on you. So as it turns out, in situations where the accelerator, where the elevator, sorry, is accelerating, go crazy on the colors here, N is not equal to W, that is, the normal force is not equal to the weight, and in fact, N is also called the apparent weight, which can be different from your actual weight, the apparent weight. So the normal, so when you talk about apparent weight, you can think of it in terms of what is the normal force acting on your body. So suppose you now look, so in a situation like this, if the elevator was at rest or moving at a constant velocity, yes, you know, it is the usual, it's the same as right now if you're sitting on a chair or you're standing up, it's whatever force you typically experience that the floor exerts on you. But there are situations where that force can be different. So now let's look at a situation where a person is riding an elevator which is accelerating up. Okay, the elevator is accelerating up, which means the person is also accelerating up. And in this situation, if I were to ask you to draw a free body diagram, so here's it's accelerating up. What you will show is, well, remember, this is a sketch from the text. You know, this is just telling the net force. Let's not worry about it. This is the free body diagram right here. You'll draw the normal force, you'll draw the weight, and as expected, you will say that the normal force is greater than your weight. Why? Because there is a net force acting on you in the upward direction. Why is the net force in the upward direction? Because that's the direction of the acceleration. The net force has to point in the direction of the acceleration. So if you call the vertical direction the y-axis, then the net force in the y direction is going to be plus n minus w, plus n because it's in the positive y direction, negative w because it's in the negative y direction. Also, we know from Newton's second law, the net force in the y direction is the mass times the acceleration in the y direction. And in this case, we know since it is accelerating upward, the acceleration is positive. So combining these two facts right here, we have n minus w equals m times a sub y, or the normal force exerted by the floor on this person or on you if you were riding the elevator would be your weight plus m times a sub y. Well, which means since the acceleration is positive, the normal force that you experience is going to be greater than your weight, and so your apparent weight, remember I said the apparent weight is just the normal force, your apparent weight, let me just emphasize that your apparent weight is in fact let's use this notation for apparent. WAPP for apparent is in fact N, which in this case, the apparent weight is your weight plus m times a sub y, or your apparent weight is going to be greater than your actual weight. So if you're standing on your weight scale, let's say it's your regular old weight scale, which tells you, or your mass scale, it'll show you a greater mass. That dial will read, show you a greater mass. Now, in terms of your experience, and this is something that you have experienced when you have an accelerator which is initially at rest and it just starts moving up, that means you're experiencing an acceleration in the upward direction. You tend to feel heavier. You can feel that on your knees. You feel that extra force on your knees, and that's because your apparent weight, or the normal force acting on you, is greater than what you are usually experiencing. Okay, so in fact, as in terms of your experience, you feel, let me put this in quotes, heavier. Okay. So here is one of your homework problems. You've got a person. Eric has a mass of 60 kilograms. You're given the mass of the person. He's standing on on a scale in an elevator that is accelerating down at 1.7 meters per second square. What is the approximate reading on the scale? So what's the weight scale going to read? Well, we've got to draw. Oh, I don't have to. There is your free body diagram for Eric. That's the free body diagram of Eric. Got the y-axis. You got the forces acting. There's the weight acting in the downward direction and the normal force acting in the upward direction. But since we know that the elevator is accelerating downward, so this is the situation where the elevator is on a top floor, and then it suddenly it starts moving down, and just that instant when it starts moving down, what do you experience? Well, if I ask you what you experience, you'll tell me that you tend to experience a little lighter, like the floor giving way. You tend to feel that. And so in asking this question, what is the approximate reading on the scale, what they are asking here is what is the normal force acting on Eric. So the apparent weight is, like I said, the same as the normal force. And in this situation, let's look at the net force in the y direction is plus n minus mg. They tell you the mass, so you can calculate the weight. It's just mass times the acceleration due to gravity. Also, we're told that the acceleration is 1.7 meters per second square, but it is in the downward direction, so we're going to stick in a negative sign right there. So let me just mark that out here just to remind you. Where did I get that negative sign? Well, the negative sign comes from reading the problem and being told that the wrong place. I'm going to make this picture a little bit more. There we go. Okay, the downward says it's negative. Now putting all this together, and I'll just remind you again, Newton's second law, applying Newton's second law. We have n minus mg equals m times a sub y, or n equals mg plus m a sub y, or you could write this as mg plus a sub y. But remember, a sub y is a negative number, and so when you work this out, so it's 60 kilograms times 9.8 meters per second square minus 1.7 meters per second square. And if you work this out, that comes out to be about 486 newtons. That is the normal force. Note Eric's weight is m times g, and that is 588 newtons. So if you compare these two facts, you can see, notice the normal force is less than the weight, or the apparent weight is less than the weight. And in fact, in terms of experience, Eric will feel lighter, or Eric feels lighter when so this is the typical scenario when an elevator starts moving downward. So if you were standing on a weight scale, what you're going to see is the weight scale displays a value less than the actual weight. So even in terms of, again, like I said, even if this is your standard weight scale that you, or a mass scale, it will read something less. It'll show you your mass is not, Eric's mass is not 60 kilograms, but something less than 60 kilograms. Okay. Just let's look at another one of these problems. Zach, whose mass, just different scenarios here, whose mass is 80 kilograms. So you're told the person's mass is given, is in an elevator. So this is kind of using some of your what we've talked about in the kinematic equations as well, whose mass is 80 kilograms, is in an elevator descending at 10 meters per second square. Call the downward direction as the negative y direction. Then your velocity is negative 10 meters per second. The elevator takes 3 seconds to brake to stop at the first floor. Okay, so it's coming down, and it takes 3 seconds. So as it's approaching the floor, it starts braking, and it takes about 3 seconds to come to rest. What is Zach's apparent weight before the elevator starts braking and while the elevator is braking? So again, reminder, apparent weight is the same as the normal force acting on Zach. Normal force acting on Zach. And the reason why I state this over and over again is the apparent weight is not a different force, a new force. It is just the normal force acting on you. Okay, and it is the reason why we use this apparent weight is because it also gives you an idea of what you experience. Okay, it's telling you what kind of force are you experiencing. Okay. So all we have to do in this is figure out the normal force acting on Zach. In part A, this is as the elevator is descending at a constant velocity, and we know that the free body diagram is going to look like this. The normal force is going to equal the weight. Why? Because the elevator is moving at a constant velocity. So what we have here is the net force. I'm just going to quickly run through this. Is it going to be plus n minus w equals 0? Why? Because since a sub y is 0, because it's moving down at a constant velocity. I'm ignoring a lot of articles there. So we have n equals w, or the apparent weight equals the weight. And for an 80 kilogram person, the weight, which is m times g, you can work this out. I think it comes out to be about 784 newtons. Part B is the one that we want to look at, where what is Zach's apparent weight while the elevator is braking? Well, if the elevator is descending and it is slowing down because it's braking and slowing down, we know from analyzing velocity and acceleration graphs, we know that the velocity and the acceleration should be in opposite directions if an object is slowing down, which means the acceleration in this case is going to be uh, um, positive. So question is, well, it doesn't really tell you the direction, the acceleration directly. It just tells you that it is descending at some speed and then it takes 3 seconds to stop. So essentially, we know that the initial velocity Vy initial is negative 10 meters per second, and also it comes to a rest, so Vy final becomes 0. Vy final equals 0 in a time delta t of 3 seconds. So using the kinematic equations, or for that matter, just the definition of the acceleration, you know that Vy final minus Vy initial over delta t. If you work this out, that's 0, and you can work this out and you'll get plus 3.3 meters per second square. So again, we didn't have to, the sign automatically came out to be positive, and you would expect the acceleration to be positive because it has to be opposite to the direction of the velocity vector. Now we come down to the free body diagram. So from the free body diagram, we have, this is plus n minus mg. And we also have Newton's second law, which says that the net force in the y direction is mass times the acceleration. And combining these two, we have n equals mg plus ma sub y. And whatever that comes out, that's going to be your apparent. That is going to be the apparent weight. Unfortunate notation, Newton is, the symbol for the Newton is n. This, well, normal force is lowercase n, just to keep that different, separate. Just to summarize what we've been talking about here regarding the apparent weight, a 50 kilogram student gets in a 1,000 kilogram elevator at rest and stands on a metric bathroom scale. As the elevator accelerated upward, the student's apparent weight measured by the weight scale is, so it is accelerating up. So if you want to, you know, from your personal experience, you know that if it's going to start accelerating up, you're going to feel heavier. So you would expect the weight scale to reach something greater than 490 newtons. So, but just going through the mathematics out here, accelerating up means net force in the y direction is in the upward direction, which means the normal force in a free body diagram, the normal force is to be greater than the weight, and so your answer here is going to be greater than 490. Now, you stand on a bathroom scale in a moving elevator. What happens to the scale reading if the cable holding the elevator suddenly breaks? Now, you don't want to get into a situation like this, and I don't want to make it sound like I want you folks to be in falling elevators. So let's change this to your physics professor. Stands on a bathroom scale on a moving elevator. What happens to a scale reading if the cable holding the elevator suddenly breaks? Okay. So, well, once the cable snaps, which means that the person is going to be accelerating, falling, or accelerating down, and the acceleration is going to be the acceleration due to gravity. So if you draw a free body diagram of the person, and this is after the cable snaps or breaks. Well, what's the free body diagram going to look like? Well, the free body diagram is going to look like just that. There is only one force acting on the person, and that is the weight. Why? Because you've got an acceleration due to gravity, so that can be the only force acting on you. So in other words, even though you may or may not be in contact with the floor doesn't do any pushing up, because if the floor were pushing up on the person, then the acceleration could not be the acceleration due to gravity. Okay, so in a situation like this, what is the normal force? The normal force, in fact, is going to be 0. Okay, and this is called, so in other sense, in a sense, the person experiences weightlessness. So the reading will drop to 0 instantly. In other words, the weight scale would read nothing. It's like the weight scale is not, or the floor is not pushing up on the person. This is called weightlessness. And this is something that weightlessness, and this is something that astronauts in space experience, and this is experienced pretty much all the time, experienced by astronauts in space, because up there, everything, the spaceship and you, the astronaut, they're all accelerating down, experiencing this constant downward acceleration of 9.8 meters per second square, which means nothing is pushing up on them, and they experience weightlessness. Okay. Again, talking about, so notice one thing that we can conclude from our discussion here is there can be scenarios when the normal force is not exactly equal to your weight. Okay, now if you're sitting in a chair right now, or if you're standing up, and I ask you what is the normal force that you're experiencing, well, you're going to tell me not the numerical value, but you'll say that the normal force is equal to your weight. Okay, assuming you're not in an elevator at this instant while you're listening to this lecture, but you'll say that the normal force is equal to the weight. But there can be scenarios, and it's not just being in elevators, there can be other scenarios where the normal force is not quite equal to your weight, is not equal to your weight. But remember, the normal force is what that floor, that surface, the force exerted by that surface on you. Okay, so here's a concept question. A box is being pulled to the right at a steady speed by a rope that angles upwards. So the rope that you see out here is at an angle theta, and the box is being moved to the right. And let's not worry about friction in this situation, just a situation like this. The question that's being asked is, how do the normal force and the weight compare? Okay, as it turns out, well, in the situation like this, if you draw a free body diagram of the box, there is the tension here. There is, of course, the weight. There is the tension. And if you notice, I've drawn the normal force less than the weight. Okay, and again, just to remind ourselves, we are not we are ignoring friction here. Now you might say, well, why is that? Why is the normal force less than the weight in this situation when you have a force, the rope, pulling at an angle? Okay, in words, I can tell you why, because the weight, which is acting in the downward direction, is being balanced by the normal force and a component of the tension in the upward direction. So what the floor does, so in a sense that the tension, the rope is kind of pulling the box off the ground, or attempting to pull the box off the ground. So what the floor has to do is slightly less than what it would do if there was no rope, or if the rope were pulling in the horizontal direction. Okay, but let's do work this out mathematically. So let's focus here. Let's focus on the net force in the y direction, just the vertical direction? Well, the net force in the y direction, there is the normal force, okay, and there is a component of the tension in the vertical direction. And let me just put that line here. Don't want to confuse this picture out here. That is the component of the tension in the y direction. And if you look at that right triangle, resolving forces into components, you know that that's going to be plus t sine theta minus mg. The weight, of course, is in the downward direction. Okay, well, there is no, in this case, there is no vertical motion. It is always in contact with the floor, which means the acceleration in the y direction is 0. And so Newton's second law applied only to the vertical motions. Newton's second law, whoops, is net force in the y direction is mass times the acceleration in the y direction, which is of course 0. So combining these two facts right here, you have plus n plus t sine theta minus mg is equal to 0, or the normal force is mg, doing a bit of algebra, taking mg on the other side, minus t sine theta. Notice what we have here. We've got the weight, that is your weight, that's the weight of the box, but you're subtracting off t sine theta. What is t sine theta? T sine theta is the component of the tension in the vertical direction. So the normal force, remember, normal force plus this vertical component of the tension has to balance the weight. So obviously the normal force is going to be less than the weight. So notice in this situation, because of this equation, notice that the normal force is less than mg, which is the weight. Okay, so your answer here, of course, is going to be n is less than mg. And again, remember, if this rope was directed in the horizontal direction, so if the force was in this, if the tension was in the horizontal direction, in that case, of course, the normal force would equal the weight, okay? Because then the normal force has to balance the entire weight, but it's because the tension was directed that way, at an angle, at an upward angle, the normal force is less than the weight. Okay, having said that much, I could say, so suppose this box was not being pulled, but rather being pushed down. Somebody was pushing down on this box, and it was sliding in the forward direction. Well, if that pushing force was directed this way, in this situation, the normal force would be greater than the weight, because the normal force now has to balance both the weight and the component of the tension in the downward direction. So the normal force would be greater than the weight. Okay. Here's another concept question. The figure shows 3 examples of the force with which someone pushes against a vertical wall. In each case, the magnitude of the pushing force is the same. Rank the normal. So you can think of, you got your hand on a wall and you're pushing on a wall. Here you're just pushing horizontally. Here you are kind of directing it in the downward direction, and here at an upward direction. But in all these situations, the magnitude of the force is, we're told the magnitude of this force is the same. So let me just put an F here to say that these forces all have the same magnitude. Now, in all these cases, the normal force exerted by, think about it as your palm, you're pushing down on a wall, pushing on a wall. The normal force that the wall exerts on your palm is going to be in exactly the opposite direction. So it's going to be, it has to, in this case, it has to balance the entire force. okay? And in fact, I'm going to say that if you look at, call this the x-axis, then this is the y-axis, not relevant to this problem, it's just the x-axis. If you look at f sub x, this, in this case, this is equal to f. Here, of course, f sub x is just that component, and here f sub x is this component right here. So by looking at the sketch, well, one thing you can conclude is that the normal force exerted by the wall has to balance the x component, and that's why we're focusing on the x component, of the applied force. Which we're calling F, okay? So in other words, N has to equal F sub X. And since F sub X in sketch C is less than F sub X in sketch B, less than F sub X in sketch A, or just to be consistent, B and A, implies the normal force in sketch C is going to be less than the normal force in sketch B, less than the normal force in sketch A. So the ranking that you have here for the normal forces is C less than B, followed by B, then the greatest is A.